We are in the midst of the proof of the measure extension theorem for finite premeasure spaces. We have a finite premeasure space. We construct the Caratea-Dori outer measure on it, which is a positive function on all subsets of the sample space. And from thence we construct the outer pseudometric. The outer measure of the symmetric difference of two sets defines, as we saw, a pseudometric on this now nice topological space. And we proved fully half of the extension theorem. That is, we showed how to extend this field to a sigma field in a natural way adapted to the premeasure. The closure of the field in the pseudometric space is a sigma field. That was our conclusion last day. The other half of the extension theorem is to prove that the premeasure extends to a measure on this sigma field. And that is what we will now proceed to do. Now, first we need to define the extension. In order to do that, we're simply going to show that this function, defined on this subset of the metric space, is sufficiently continuous that it automatically extends to the closure. Let's see how we do that. We've already proved last time that on the field, the outer measure restricts to the premeasure. Using that fact, we can note that the distance between any two elements A and B in the field, which is defined to be the outer measure of the symmetric difference, is just the premeasure of the symmetric difference of those two sets, because the symmetric difference of two sets in a field is back in the field. Now, there are many ways we could write down and estimate the measure of the symmetric difference. Let's look at this picture right here. Notice that the symmetric difference, which is the shaded region, is not so far from the union. In fact, we can see from the picture here that the missing piece is the intersection of A and B. So that shows us that the measure of the symmetric difference of A and B plus the measure of the intersection of A and B, which is disjoint from the symmetric difference, is equal to the measure of the union. Thus, the measure of the symmetric difference is the difference of the measures of the union and the intersection of the two sets. Now, notice that the measure of the union is greater than or equal to the measure of B. The measure of the intersection is less than or equal to the measure of A, and so its negative is greater than or equal to negative the measure of A. Similarly, we could reverse the roles of A and B there, and instead conclude this. So since both of those inequalities are true, we actually see that this is greater than or equal to the absolute value of the difference between mu of A and mu of B. And what that tells us is precisely that mu is a lip-1 function on the set A. Now it follows directly from there that mu has a unique lip-1 extension to the closure. There is our extension. It is a Lipschitz function defined on this closed set, which also happens to be a sigma field. Our goal is now to show that that extension is in fact a countably additive measure on this sigma field. And we're going to do that using topological considerations. So as a first step, we'd like to gain a better understanding of the structure of the closure. To see that, we're going to define a very useful class of sets extending any given set. start with any collection of subsets of some set omega. This is very useful notation. For any class E, E sigma is the set of all countable unions of elements from E. So if E was a sigma field, then E sigma is just E. But if E was the field A, then E sigma is typically going to be larger than E. Now note by definition that E sigma is automatically closed under countable unions, because a countable union of countable unions is a countable union. What's more, E sigma is closed under finite intersection, provided that the set E is closed under finite intersection. And that just follows from De Morgan's laws again. If I take the countable union of some sets EI from E, and another countable union of some sets Fj from E, and I take the intersection of those, that can be written instead as the union over I and j ranging from 1 up to infinity of EI intersect Fj. Now, if the set E is closed under intersection, then this set will be back in E, and therefore this is a countable union of sets in E, and so it is in E sigma. Now, with that useful notation in hand, we can restate a lemma that we proved last time as follows. Suppose we have a finite premeasure space, as usual. Then the statement is that A sigma has the same closure as A in the pseudometric. And moreover, the Lipschitz extension of the premeasure coincides with the outer measure, not just on A, as we already proved, but on all of A sigma. That's going to be critical to our proving that this is actually a measure. So, why is this true? Last time we showed that if a sequence of sets in the field increases to A in omega, then in fact AN converges to A in terms of the pseudometric. And moreover, the distance between AN and A can be written as the outer measure of A minus the measure of AN. Now, suppose that I have a set A which is in A sigma. That means that A can be written in the form countable union of some sets Bn that are in the field. But if I define AN to be the sum of the first n bj's, it then follows that AN increases to A. And so we can simply plug in over here and conclude that A is the limit of a sequence in A. And that means that our set A, which was arbitrarily chosen in A sigma, is in fact in the closure of A. So that shows that A sigma is contained in the closure of A. But A sigma also contains the field A. And it follows from this, taking closures, that the closure of A sigma is squeezed in between the closure of A and the closure of A, which is the closure of A. And that shows us that A sigma and A indeed have the same closure. As for the second statement, that mu star and mu bar agree on all of A sigma, we simply note that now knowing that A sigma is contained in A closure, this identity here shows us that mu star of A, which is the limit of the ANs, is therefore the limit of mu of the ANs. Now, mu is our original premeasure, and its extension is the unique Lipschitz extension of mu from A to A closure. Here, we have a sequence, AN, which converges to A, and since the extension of mu is a continuous function on the closure, by continuity it follows that this must be equal to mu bar of the limit. In fact, that's how the extension of mu bar is even defined. And that shows that mu star and mu bar agree on all of A sigma. So mu bar and mu star agree on A sigma, which is typically strictly larger than the field A. Ultimately, we want to show that in fact they agree on all of A closure, which we now know is the same as A sigma closure. So that begs the question, how different is A sigma from A closure? Well, in general, A closure, a sigma field, will be much larger than A sigma. A sigma is closed under countable unions, but not under countable intersections. And so we would need to take the closure under countable intersections, and then take this new set and close it under countable unions, and so on down the line transfinitely, in order to get all the way to the sigma field generated by A, which may in fact be smaller than this sigma field. So in a set theoretic sense, these two are probably quite different from each other. But in fact, we can use this set to approximate this set in a way that will allow us to do this extension quite easily. And here's how. Again, in the context of a finite premeasure space, we have the following characterization of the closure of A. A set B in omega is in the closure if and only if it can be approximated from the outside by elements of A sigma. To be precise, for every tolerance epsilon, there is some set C in A sigma containing B, so that the outer measure of B minus C is smaller than epsilon. Or, alternatively, we can think of it as the distance between B and C being smaller than epsilon. Let's prove this. One direction is quite straightforward. Suppose that we have this approximation property. That is, we can approximate B from the outside by elements of A sigma. Well then, for each n, choose a Cn in A sigma such that the distance is less than 1 over n. Epsilon is being taken to be 1 over n here. This, of course, shows that the sequence Cn converges to B. And so that shows that B is in the closure of A sigma. But as we showed on the previous slide, that's the same as the closure of A, and so therefore we get that 2 implies 1. Now for the reverse. Suppose that B is any set in the closure of A. We want to show that we have this property 2, this outer approximation property. So let's fix our tolerance epsilon. And by the assumption of part 1 that B is in the closure of A, we know that we can find some set G that is in the field A such that the distance between B and G is smaller than epsilon. And note again that that distance is defined to be the pseudometric outer measure of the symmetric difference of B with G. Okay? Now let's revert to the definition of the outer measure. The outer measure of B symmetric difference G is the infimum over all countable sums of premeasure of sets AN in the field where those ANs are chosen so that the set B symmetric difference G is contained in the countable union of the ANs. So we see that the infimum of this set of possible sums is strictly less than epsilon. That means that we can achieve a value for such a sum less than epsilon with some sequence. We can find a countable sequence in the field A such that B symmetric difference G is contained in the union of the ANs, and the sum of the pre-measures of the ANs is smaller than epsilon. Okay, well, what we'd like to do is construct some set that contains B, not B symmetric difference G. And so in order to achieve that, we'll just throw G back in. So we'll set C to be the union of G with this countable union of the ANs. Now notice that that whole thing is a countable union of sets that are in A. And so C is in A sigma. And moreover, the original set B is certainly contained in B minus G union G. And B minus G is contained in the symmetric difference of B and G. So this whole thing is contained in the symmetric difference of B and G union G. And that is contained in C because B union G is contained in the union of the ANs by construction. So we do indeed have that B is contained in C as desired. So we just need to check, to conclude the proof of part 2, that the distance between B and this set C is less than epsilon. Well, if I look at C minus B, that's equal to G minus B union with the union of the ANs minus B. And G minus B is contained in the symmetric difference of B and G. And now we see that that union is certainly contained in the union of the ANs. Each of the two terms is contained in the union of the ANs. Okay? And therefore, the outer measure of C minus B, which is the infimum over the sums of the premeasures of all sets in any union that's countable that contains it, that infimum there includes this set of ANs, which means that that is less than or equal to the sum of the premeasures of the ANs, and that was what we arranged to be less than epsilon. And that concludes part 2. And so we have our characterization of the closure of A as those sets that can be outer approximated by elements of A sigma. That now allows us to prove the desired statement that mu star and mu bar agree everywhere on A closure. Okay. So let's see why that is true. Fix any set B in the closure. We would like to show that mu bar of B is equal to mu star of B. We're going to show that by showing that each of those two is less than or equal to the other. For the first inequality, notice that mu bar of B is the same thing as mu bar of B minus mu bar of the empty set. I've written it this way because we're going to use the fact that mu bar is a Lipschitz function with constant 1. That difference is less than or equal to the pseudometric distance between B and the empty set, which is just defined to be mu star of B's symmetric difference with the empty set. Of course, symmetric difference with the empty set just gives us B again, so that's mu star of B. And there is the first inequality. Mu bar of B is less than or equal to mu star of B. We didn't need any information there other than the lip 1 nature of mu for that. Now for the reverse, we're going to use the outer approximation property we just proved. Okay, so fix a tolerance epsilon and choose a set C that is in A sigma, which contains B, and for which the distance between B and C, which is the same as mu star of the symmetric difference of B and C, but because B is contained in C, that's just C minus B, such that that is less than epsilon. We know that for any set B in the closure of A, we can find such a set C for any tolerance epsilon. Okay? Well, thence we have, from similar Lipschitz considerations, mu bar of B minus mu bar of that C is, in absolute value, less than or equal to the pseudometric difference between B and C, which we've designed to be less than epsilon. Okay? And from there, we get that by taking off the absolute value bars and comparing the terms in the order we know they come. The extended measure mu bar of C is less than or equal to the extended measure mu bar of B plus epsilon. But C is in A sigma. And we just proved that mu bar and mu star agree on A sigma. So this is the same as mu star of C. Of course, B is contained in C, and mu star, the outer measure, is monotone. So mu star of B is less than or equal to mu star of C. And from what we proved in the first inequality, mu bar of B is less than or equal to mu star of B. And so that shows that mu star of B is squeezed in between mu bar of B and mu bar of B plus epsilon for any epsilon we care to choose. Therefore, taking epsilon down to 0 shows that mu bar of B is equal to mu star of B for any B in the closure of A, concluding the proof. Great. So now, let's take it home. We are finally ready to conclude the proof of the measure extension theorem. If mu is a finite premeasure on the field A, then the Lipschitz extension of mu to the closure of A is a full-fledged, countably additive measure on this sigma field. Let's prove this. Ironically, it really boils down to showing that mu bar is finitely additive. Because if we can show that it is finitely additive on the field A bar, we know from early on that it is countably superadditive. However, we just showed that mu bar and mu star coincide on A closure. And mu star, the outer measure, is countably subadditive on all of 2 to the omega. And so that means that mu bar is both countably superadditive and countably subadditive on A bar, and is therefore countably additive there, showing that it is a measure. So we need only show that mu bar is in fact finitely additive. And that will follow very easily from its definition as a continuous extension of mu, which is finitely additive. Let's write down the details. Let's fix 2 sets, A and B, in A closure. Since they're in the closure, we can find sequences AN that converge to A and BN converge to B, where the AN and the BN are in A. Now, let's look at the union and the intersection of the ANs and the BNs. Last time, we proved that if we have a countable union of sets in A, then the distance between that countable union and another countable union is bounded by the sum of the distances between the individual terms. Well, here we have a finite union. If you want, we could just consider these with an infinite collection of empty sets unioned afterward, or the second one with an infinite collection of an afterward. Therefore, we can look at the distance from an union bn to a union b, or the distance from an intersection bn to a intersection b, and both of those will be less than or equal to the sum of the distance from an to a and the distance from bn to b. And both of those were chosen to go to 0. Therefore, we see that an union bn converges to a union b, and an intersect bn converges to a intersect b. And therefore, mu bar of a union b plus mu bar of a intersect b, well, that's just the limit, as n goes to infinity, of mu of an union bn plus mu of an intersect bn. But mu is a finitely additive measure, and that means that it satisfies the strong additive formula that the measure of the union plus the measure of the intersection is the sum of the measures of the two sets. And now that limit is, of course, by definition, equal to mu bar of A plus mu bar of B. That shows that mu bar also satisfies the strong additive formula and is therefore finitely additive, and that concludes our proof of the measure extension theorem for finite premeasure spaces.